All right, so I will quickly present a couple things we do at AVIA that highlights a couple different aspects of disease and vector modeling related where Earth observation data comes in. Oh. No, now it's working. So basically we work around three things. So I will give the example of vectors, but it's the same for diseases. So one is, where is the vector? When will the vector be active? And how many of the will there be? But we can do this for diseases too. We do for dengue, for example, where will be outbreaks? When will the outbreak be, and will it be big or small? Basically the cases related to the outbreak. For the where, we actually quite a while ago now developed a software package with financial aid from ESA, funding from their business application program, to help people to find, collect data in the field and then model where vectors will be. So this is where we will use the field data collected together with Earth observation covariates, like, for example, the NDVI that you might have seen in the tour early during the lunch break, together with other covariates to model the distribution of a certain disease vector. We can do this in different scales, and that's where the spatial resolution of Earth observation becomes very important. You want to make sure that the resolution of your Earth observation is matching your data. So if you have very local data, like I give the example of Brazil here, you want to have a higher resolution Earth observation product that will match the data you have. Otherwise, you will not get the full information available in your data. As you can see here, if you would use a coarser product, it would level out much more the information you have compared to if you would use a higher scale product. And this can go, if you would go more local, this of course increases as well. Another aspect is that if your disease data often does not match the Earth observation, as disease data is, especially if you talk about humans, but I give an example here for tick disease in dogs, is that it's often aggregated to a certain admin level, while Earth observation always comes in grids, and therefore it requires extra processing to be able to use and either have an output in admin level or in a spatial grid, depending on further applications, of course. But there's a disconnect between the two. If you want to know more, we can discuss more, but I have very little time, so I will skip. So for vector seasonality, so when the vector will be active is actually quite straightforward, and then it's very easy to, well, easy. It's very well doable together with Earth observation, where we will use something like a Sentinel platform or a Modospheres platform to model the activity of the vector throughout the season, and so we can estimate start of season and duration of the season, etc. As a last slide before my time runs out completely, if you want to go, okay, if you want to go more in a more detailed approach, and you want to know how many vectors or how many cases of a disease will you want to predict the abundance, basically. You want to have either very high scale resolution Earth observation data, or you want to have Earth observation data that you then correlate together with local measurements, which is something we do, for example, in the French overseas territories for our dengue work there and our ADIS work, is where you have the current available satellite products, but you can then correlate that with local measurements that we then developed with another funding from ESA, actually, and local measurements where we then with SATCOM can also deploy those in very remote areas where currently, for example, cell reception, for example, is unavailable. I present this is for vectors, but we do the same for diseases in Latin America and in Southeast Asia, but we also work together with ECDC for the ADIS risk project, for example, for dengue in Europe. So that's it.